Welcome back to the Design by Analysis series. In the last video, we solved PTB-3 example for protection against plastic collapse using elastic limit load and elastic plastic methods. In this third video, we will continue our journey through part 5 of Division 2 and now focus on another critical failure mode, protection against local failure. We will again use PTB3 examples, specifically example 5.3.2 and 5.3.3 to see how ASME requires us to evaluate local failure using both elastic analysis and elastic plastic analysis. Just as before, I'm referencing the 2025 edition of ASME Section VIII Div 2, so section or clause numbers may be slightly different from older versions. Also, there may be small difference in the results because PTB3 doesn't provide CAD geometry. We must recreate the model from the given dimensions, which can lead to slight variation. First, let's look at the elastic analysis example. Our first problem is PTB3 example 5.3.2. Uh, we need to demonstrate protection against local failure for component that has been designed using design by analysis rules in accordance with ASME Section 8 Div 2 Part 5. As required by clause 5.3.1, since the component's wall thickness and geometry were not selected using the Part 4 rules, it must be assessed for local failures under the applied design load. The objective is to perform an elastic analysis as per clause 5.3.2 and check whether the calculated triaxial stress remain below the allowable limit, which is 4 times the allowable limits derived from material properties. The design pressure is 420 psi, model reused from example 5.2.1. The same model and material condition were used as in example 5.2.1. The head and shell of the pressure vessel are made from SA516 material and the top forging is made from SA105. S is the allowable stress from section 2D, Sy is the yield strength, St is the tensile strength, E is the modulus of elasticity, nu is the Poisson's ratio. These values form the basis for all stress checks. The criterion for local failure in elastic analysis is based on principal stresses. The algebraic sum of three linearized primary principal stresses must be less than or equal to 4s, where s is the allowable stress from section 2D. Triaxial stress limit is sigma 1 plus sigma 2 plus sigma 3 should be less than equal to 4s. For example, for SA105, the allowable stress is 23.3 ksi and 4 times of that value is 93.2 ksi, which we can see here. The allowable value is 23.3 and if we multiply by 4 times, we'll get 93.2. This ensures that hydrostatic stresses does not exceed the allowable ductility of the material. This is a check for volumetric hydrostatic stress collapse, which can lead to gross yielding or failure due to excessive hydrostatic stresses, even if von Mises is within the limits. It also uses the linearized stress components, membrane plus bending, for three principal stresses, excludes secondary and peak stresses. That's why, when performing the elastic local failure check, you don't use total stresses or secondary or peak components. Instead, you linearize along an SCL and take the primary membrane plus bending values for three principal stresses, then check the stress limit criteria. We reuse the same finite element model developed earlier in example 5.2.1, a 2D axisymmetric model with internal pressure of 420 psi applied. Boundary conditions are the same as before, with constraints that allow the vessel to expand realistically. The FEA results were checked against the criterion. In FEA, user-defined results are obtained with the expression S1 plus S2 plus S3, which are principal stresses. This includes all stresses, including bending, membrane, and peak. The total principal stress sum, including membrane, bending, and peak, which is 74.195 ksi is less than the allowable value of 93.2 ksi. Here you can see the expression is S1 plus S2 plus S3 and the value is 74.1, which is less than the allowable limit of 93.2 ksi. This means that even the unlinearized results already satisfy the code. Therefore, stress linearization was not part in this case. You can compare the stress distribution with PTB-3 figure 5.3.2.1. The results are in excellent agreement. The elastic local failure criterion uses the sum of three principal stresses, S1 plus S2 plus S3, which is also known as the first stress invariant or I1. This value is the trace of the stresses tensor and it represents the hydrostatic or mean stresses. Hydrostatic stress contributes to volumetric change but not to distortion. That's why ASME checks this quantity against 4s to make sure the vessel does not fail due to excessive volumetric loading. The contour plot you see here is sum principles and it directly shows this invariant across the component. This confirms that the vessel passes the elastic local failure check under the design pressure of 420 psi. Now let's move on to the elastic plastic analysis example, which is 5.3.3 elastic plastic analysis. Our second problem is PTB-3 example 5.3.3. Again, we must demonstrate protection against local failure as required by clause 5.3.1, but this time using the elastic plastic analysis method in clause 5.3.3. The objective is to compare the calculated equivalent plastic strain against the limiting triaxial strain defined in the code. The material remains the same as before. Strain limit is algebraic sum of equivalent plastic strain EPQ and cold forming strain ECF should be less than limiting triaxial strain limit, which is EL value. The triaxial strain limit prevents failure from excessive plastic strain in high constraint regions. It ensures that even if yielding has occurred, the total accumulated plastic deformation does not exceed the material's ductile capacity under combined effect of all three principal stresses. For local failure, the code requires that the structure withstand a local load factor of 1.7p. That means the vessel must survive at least 714 psi, which is 1.7 times the design pressure of 420 psi, without exceeding the strain limits. This requirement comes from table 5.5 of division 2. We reuse the same finite element model developed earlier in example 5.2.1, a 2D axisymmetric model with internal pressure of 714 psi applied. Boundary conditions are the same as before, with constraints that allow the vessel to expand realistically. By following 5-step method, it becomes very easy to check protection against local failure using elastic plastic analysis method. The step 1 is find principal stresses, equivalent plastic strain and stresses. You can also check with using equation 5.1 or FEA. Step 2 is find strain limit parameters, which is R, alpha SL, M2, epsilon ELU, which are used in EL, which is limiting triaxial strain using table 5.7. Step 3 is find limiting triaxial strain using equation 5.7. Step 4 is forming strain based on material and fabrication method in accordance with part 6. Step 5, which is the final step, is to check strain limit criteria using equation 5.8. Now we'll go to the steps one by one. Here the step 1 is to extract stresses and strains. Step 1 is to perform an elastic plastic stress analysis and extract stresses and strains from the FEA results. The effect of nonlinear geometry is considered in the analysis. The same model and material condition were used as example 5.2.3. Only pressure changes to 1.7 p according to table 5.5. For a critical node location, as shown in the example, is considered in this example. I have selected the same node as used in the PTB-3 example. At this node, you will get sigma 1 of 42.3 psi, KSI, sigma 2 of 33.8 KSI. The values are in PSI, but I'm saying in KSI. And sigma 3 as 955 PSI, and the equivalent stress as 38.9 KSI. And also you get a equivalent plastic strain of 0.0024825 at this location. Step 2 is to collect strain limit parameters from table 5.7. In this case, both the materials SA105 and SA516 falls under ferritic microstructure, and for that case we used, according to ASME table 5.7 category, we use ferritic steel, and we can get the values of R alpha M2 ELU. The R is the ratio of yield stress versus UTS stress, and they will be different for both of the materials. And alpha and M we can get from the table. ELU is same as M2, because if the elongation and reduction area are not specified, we use them same. Step 3 is to calculate the limiting triaxial strain using equation 5.7 of div 2. Here all the variables on the right hand side of this equation has been obtained in step 2 and 3. By substituting, limiting triaxial strain becomes 0.155 for that node. Step 4 is to determine the cold forming strain. Forming strain is determined based on material and fabrication method in accordance with part 6. If forming is performed in accordance with part 6, the forming strain may be assumed to be 0. For this case, the heat treatment assumed, the forming strain is taken as 0. Finally, step 5 is to check the code criterion. Check strain limit criterion, which is algebraic sum of equivalent plastic strain and cold forming strain, should be less than limiting triaxial strain limit, which is EL. Limiting stress strain limit is 0.1515 we obtained in the previous slide, and equivalent plastic strain is 0.0024825, that also we obtained in the previous slide, which is less than the limiting strain, and hence the criteria is satisfied. Also, the maximum strain limit ratio was only 0.018, which is well below the value of 1.0. Limiting ratio, we can see it here. Just to clarify, I didn't use the maximum value of plastic strain from the plot. I used a value at different location. Therefore, you would see the plastic strain value used in criterion is 0.0024825, not 0.0027424. This is just to match the location PTB3 example used for criteria check. Contour plots of equivalent plastic strain and strain limit ratio can be compared with PTB3 figure 5.3.32 and 3. They are in very good agreement. To summarize, elastic analysis confirmed that hydrostatic stress remained below 4s, satisfying the code requirement. Elastic plastic analysis showed that equivalent plastic strain plus cold forming strain is far below the limiting strain. Together, these methods demonstrate that the pressure vessel is adequately protected against local failure. This exercise shows how ASME Part 5 checks extend beyond plastic collapse and addresses ductile capacity under multi-axial stresses. In future videos, we'll move on to the next design by analysis failure modes in Part 5 of Div 2, which are buckling, cyclic loading, and creep. For each of these, we will again solve PTB3 examples step by steps. This way, you will not only understand the DBA methods, but also learn how to confidently apply it in real engineering application. As always, please remember, these examples are presented here for educational purpose only. For actual design and compliance, you must refer to the official ASME boiler and pressure vessel code and PTB3 documentation. If you found this video useful, please like, share, and subscribe so you don't miss the upcoming lectures. A lot more clear, practical, knowledgeable, packed content is on the way. Thank you.